Hello again, physicists. Today I bring to you the circles of Daytona. We're going to look at probably the most common form of circular motion that you experience on a day-to-day basis. I'm talking about being in a car and taking a turn. When the car turns, that is circular motion. You do not necessarily need to travel in a complete circle. It could be a turn that creates a quarter circle, an eighth of a circle, or any sort of curvature of motion that makes it circular. So we're going to look at two specific cases where you can be in circular motion, and based on the case, it'll affect what is the center-seeking force, what is our centripetal force, where is it coming from. So for the first case, we'll look at your most standard situation where the car is on a flat roadway and it is making a turn. In this case, if we look at the free body diagram over on the right, you can see that we have three forces acting on the car. We have the gravitational force of the car pulling down, we have the normal force of the roadway pushing up on the car, and then we have the force of friction between the tires of the car and the road. It is the force of friction that is actually providing us with that centripetal force. So if we look at the top view right underneath our free body diagram, you can see that if this is the curvature of the motion, then our center of our circle would be somewhere over here, and friction indeed is pointing towards the center. So there is your centripetal force. Let's look at the derivation to see then, okay, well, how fast can you go on a turn? Because you've probably known or seen from the movies that if a car takes a turn too fast, the car will go flying into the air or just go flying off the road altogether. So we're going to start with the same equation that we've been using, Newton's second law. We just need to remind ourselves that when we're talking about circular motion, the net force will be for centripetal forces, and the acceleration we're talking about is centripetal acceleration. If I substitute in for the centripetal acceleration with the speed squared divided by the radius, and also substitute the net force in for the force of friction, because our free body diagram told us that that is the centripetal force here, this is what I would have. Well, I can go a step further. I can make substitutions for what the force of friction would be. Since I'm on a flat surface, I know that my normal force will be the same as my gravitational force, mg. So I can say that the force of friction will be the coefficient of friction times the normal force. And I can go one step further and say, well, that will be mg, and you'll see that the mass of the car will drop out of the equation. And basically what we're left with is saying that the speed the car can go at will be dictated by three things: the acceleration due to gravity, the coefficient of friction, and how wide the turn is, the radius of the turn. And basically, the higher each of those three variables are, the higher speed you can take going into the turn. If you think about the coefficient of friction factor, it kind of makes sense that you need a higher coefficient of friction to take a turn at a faster speed. That's why when it snows, or when you have freezing rain and the road conditions aren't ideal, you need to take turns much slower because the coefficient of friction between your tires and the road will be much lower. Also, when you're trying to do a very tight turn, like an on-ramp to a freeway, that's a very small radius of a turn to take, and therefore you need to decrease your speed significantly. Whereas if you're on a very large turn on a road, you can pretty much maintain your regular speed without any issue. So again, this is kind of showing you conceptually how circular motion works when you're in a car on a flat road surface. Next, we'll look at a case where maybe you want to be able to go faster on a turn and you really can't change anything about the roadway. In some particular cases, like a place where you have limitations on how large of a turn you can take. This is common when you're building a freeway on-ramp or off-ramp, as well as extreme cases of speed in a car, such as NASCAR. You're going to want to somehow come up with a different way to provide centripetal force, because with friction, you have issues such as, well, the roadway conditions can dramatically affect how fast you're able to drive. If it rains, you have to go slower. If it snows, you have to go slower. A way that engineers can get around that problem is by actually banking the road. In other words, instead of the road laying flat like it was before, you actually have the roadway tilted at an angle. So this would be a face-on view of a banked road. You can see it's actually kind of like an inclined plane. Now, I'm not going to get into the gory details as to how it all shakes out, but essentially, you now have a different force providing that centripetal force to keep the car going in a circle. And it'll be a component of the normal force. So this component right here of the normal force would be pointing towards the center of the circle the car is driving in. And this would provide you with your centripetal force. So over here, I just did a little math here. So first I figured out what is the normal force in terms of the weight of the car as well as the angle of the incline. And then doing a substitution and a little bit of algebra, what it shakes out to now is that how fast you can go on a banked turn versus a flat turn won't depend so much on the coefficient of friction, but instead will depend upon, well, how banked is the turn? What is that angle? And this usually lends to, as I already said, cars being able to travel at a much higher speed. So there you go, a little bit of circular motion, and when it comes to driving. Until next time, physicists, until next time.